Good evening. Shortly we will hear an interesting lecture by Professor Ibrahim Abdul-Halim on plasmonic biosensors. This is part of a webinar series organized by Photonics Israel on various aspects of photonics. The photonics industry is a technological and economic growth engine in the world. In Israel, it contributes about $6 billion annually to the economy. Photonics Israel operates within Engineers Association as a cluster of photonics entities. Since we started operating last year, we have established close relationships with similar clusters in the US and Europe. Our mission is to deepen the knowledge in this area and to encourage cooperation both within Israel and with photonics entities in the world. We are open to your suggestions and would love to help foster new local and international collaborations. My name is Shlomo Glaser and I'm the manager of Photonics Israel. Ibrahim Abdul-Halim is professor at the Department of Electro-Optics and Photonics Engineering at Ben-Gurion University. He headed the department between 2007 and 2015. Professor Abdul-Halim currently research involves LC devices for imaging, nanophotonics and plasmonics for biosensing and biomedical optical imaging techniques. Professor Abdul-Halim, the floor is yours.
Thank you, Shlomo. Good evening, everyone. Good morning for some of you. Okay, as mentioned, we'll be talking about surface plasmon resonance biosensors. And after giving an introduction on plasmonics, I will talk about the general idea of sensing using evanescent waves and why it's important for specific sensing. Then we'll talk about extended versus localized plasmons. For example, periodic arrays of nanofeatures, which can excite both extended and localized ones, about the field enhancement, the local field enhancement, which is very important. It's correlated with the sensor sensitivity and important for enhanced spectroscopy, such as SERS and CEF, and we'll present some substrates among the most important ones, and some we have been working on, and we'll show some applications, environmental and medical, and then summary. So motivation for biosensors in general, it's very important for human health, as we realized lately because of the corona outbreak. But apart from that, there are many other applications, environmental pollutants, which can endanger our health, for example, in water or in air, in agriculture, and so on. Of course, blood analytes detection, like biomarkers, for example, for diseases, for cancer. It has applications as well in drug discovery, research, development of, let's say, drugs, or because we need to know the binding of one molecule at the drug to a certain molecule and how strong it is as compared to others. And of course, food inspection and many, many more applications. So biosensors or chemical sensors in general have many applications, and they have been occupying the efforts of many researchers and many startup companies for many years. Apart from the importance, there is also with that coming the market, which is quite a huge market. Biosensors in general is around 31.5 billions will arrive at 2024. with 8% increase per year. The plasmonic ones, we can say they are just starting, and they are a small fraction of it. The majority are electrochemical ones, but I think plasmonics, optical ones are rising as almost with everything where photonics is entering as the new or the 2020 technology, let's say, replacing many other electronic techniques. So there is a lot of motivation behind biosensors. Okay, so what about plasmonics? First of all, there is the field enhancement, which is the key issue actually in most of the plasmonic effects, including biosensing, the fact that we can focus or concentrate the light behind a nanotip with the intensities million times, sometimes more than any other way of focusing, such as using diffraction limited optics, for example, lenses, microscope objectives, mirrors, and so on. So the key factor is the enhanced local field near nanostructures, which correlate, we will show that it correlates with the sensor sensitivity. It's a evanescent field, so it can help in specificity and selectivity of the sensor. And of course, it has many other applications. We will not go in details to many of them because our main goal is talking about biosensing. But of course, field enhancement is important for enhancing the efficiency of optoelectronic energy devices, for material research, molecular optics. Of course, surface enhanced spectroscopy, also used both as a research tool and as sensing methodology, using nanoparticles for cancer therapy and diagnostics is well known now, biological research, and of course, photonic circuits when we combine plasmonics with silicon technology, for example, and many, many more applications. Okay, so let's start from the basics. When we talk about evanescent field, the first thing we think about is total antenna reflection. That's the easiest case when we have light coming from a denser medium with a refractive index N1 larger than N2, then above certain angle, we get total antenna reflection, and the light cannot propagate inside the second medium. But the field is evanescent within fraction of the wavelength. We can calculate easily, called the penetration depth, and it decreases as we increase the angle, the incidence angle. It can be as small as lambda over 10 or even less. And we can see this effect in many other optical phenomena. For example, what's called whispering gallery modes, where we have this these waves circulating a sphere. We can excite surface waves. For example, what we are talking about now is when we have a metallic film, we excite the plasmonic wave, and it's a wave propagating along this surface, but cannot propagate perpendicular to the surface. So it has an evanescent field, and this evanescent field can feel what's happening near the surface within the penetration depth, of course. So it is important, this penetration depth is highly important as it can easily sense small entities like molecules, proteins, viruses. But if it's large entity like large cells, bacteria or blood cells, which can be like 10 micron cells, then it's a bit problematic because there is no overlap between the whole cell and the evanescent field. And of course, you can excite surface wave with many other configurations like gratings, with a grating coupling, with fibers, waveguides, and so on. So the evanescent field is the key issue for specific sensing. Why? Because we can have many analytes inside a medium. You can have many shapes. I mean, this is only diagrammatic, but let's say a variety of molecules. If we want, how can we know what we are detecting? The fact that the field only exists only near the surface, and we use this fact by coating the surface with a binder or receptor layer, such as an antibody, aptamer, or peptides, which are designed to receive or to bind only to one specific molecule. Let's see if it has, it's according to the geometry, it will be fitting very well to this yellow type body or entity. So we are, because we are sensitive only to what's happening near the surface, this way we can convert the sensor to be specific and not simply a refractive index sensor of a bulk, right? So anything away from the penetration depth will not be sensed. That's the idea of using evanescent wave sensors for specific sensing. Okay, so with plasmonics, we can distinguish two main plasmonic waves, the extended one and the localized one. The extended one can be excited using a coupling medium, for example, prism, a grating, and we need a continuous film of metal. And the following certain conditions, which we will be showing very soon, we will excite the wave and get this evanescent field inside the medium which we are interested to sense. The other option is using nanoparticles or nanostructures, and then the wave can be excited because the particle is kind of scattering. You get scattering from the particle, and this helps excite the surface wave. But the surface wave then is localized on the surface of the particle, cannot propagate along the metal film, as in this case. So that's why it's called localized surface plasmon resonance. In both cases, we are looking for a minimum in the spectrum. Let's see, in this case, we look for reflectivity, and we see a minimum if we scan the angle or the wavelength. And this minimum is very sensitive to the environment, the refractive index of the analyte medium. The same with this one, but here we don't do it as function of angle because it's scattering and does not, it's usually a random medium. It does not make sense to measure it as function of angle. We measure it as function of wavelength and look for the extension of what's called the minimum in the reflectivity or transmission, or 1 minus reflectivity minus transmission, which is kind of the absorption plus scattering effects. We see a minimum, and this minimum is again sensitive to the refractive index of the medium. There are major differences between the two types. For example, in this case, the penetration depth is more or less similar to the total internal reflection. It's determined by the metal properties as well, not only the coupling medium or the analyte medium. but it's a fraction of the wavelength. And we get, because the field is confined, again, here in this direction, we get enhancement near the interface. And this enhancement is something like times 10 to times 20, but it has very high sensitivity in terms of shift of the wavelength of the resonance could arrive to 50,000 nanometers per refractive index units, which is very, very large. It's a huge number as compared to the localized SPR, which is only 100 up till 500 nanometers per RIU. However, the field enhancement is larger in general for like a sphere or a regular shape. It's around 20 till 100. But we can make it even higher, for example, make very sharp corners or play with the periodic structures or other types of nanostructure. You can enhance the field even more. And the most important is that the penetration depth here is only at the nanoscale, the very nanoscale, like 20 nanometers, very near the nanoparticle. So it is good actually for small bioentities like molecules, proteins, maybe viruses. For large ones, it is a bit problematic. We need tricks to do that, maybe indirectly. And we will show some cases, for example, using SAFE or SARES. Okay, I will go on with the extended SPR first, then we'll switch to the LSPR. First, about the conditions to excite the SPR. So as mentioned, we need a coupling medium because the wave vector of this surface wave is given by this expression, the real part of this expression. And apparently this wave vector is a bit larger than the wave vector of light coming from free space. So we need to enhance the wave vector along the surface in order to get matching with this wave vector of the surface wave to have it excited. And we can do that by coming through a prism, for example, because of the edge of the prism. We can have here relatively large angle. And if the refractive index of the prism is large enough, we can meet this condition. So the K vector along the X direction in the prism will be this one, times the 2 pi over lambda n of the coupling medium times sine of the angle. However, we can do it also with a grating, right? The grating gives some momentum because of the grating wave vector, depending on the diffraction order. And it's something like 2 pi over the period of the grating times the diffraction order. So we can, if we come at an angle, we have this contribution from the angle. Then we add to it the grating wave vector, and that's enough usually to excite the plasmon, even with the first order beam. And so on, we can do it, of course, if we can do it with a prism, it means we can do it with a waveguide, or we can do it with a fiber. And there are some other ways, for example, what's called, it's a prism, but auto configuration rather than enrichment. With the auto, we have a bulk conductor slightly away from the prism within the penetration depth of the evanescent wave, so that possible to excite this wave along the metal surface. In this case, we have a thin film of 40 to 50 nanometer, and that's good enough to excite it on the surface of it. And it's easier to implement rather than the auto configuration. If we take simply the wave equation or Maxwell's equation, then it's very easy to show that you can excite the plasmon wave only with transfer of magnetic polarization, which means the vector of the electric field is in the plane of incidence, so that it has a component perpendicular to the metal surface. That's important in order to be able to bring the charge to the surface. With the TE configuration, the polarization, we have only one component, and it's tangential to the surface along Y. There is nothing perpendicular to the metal, so we cannot produce the charge. So that's why the SPR with the extended configuration can happen only with TM polarization. So this is the first condition. We need a polarized light in the TM, or have a polarizer. Of course, with the localized SPR, this condition is relaxed because it's based on scattering, and polarization can happen in both polarizations. The second condition is more related to the K vector we mentioned. K vector is like the momentum of the photon, and that's easy to show if we take the TM polarization, which has E in the XZ plane, and then H will be in the Y direction. And we look for a wave which is exponentially decaying in Z. If we find a condition where this can happen, it means we have this evanescent wave along Z, but it is propagating along X. So if we plug this into Maxwell's equations, we find this one, from which we can easily find that we find Kz, and then from this one we find Kx, which is the K vector along the X direction of this type of wave, which is decaying in Z. So this is the surface plasmon wave, and it has, you can easily see that in order to have the wave, propagating along X, to have some propagating distance, you need to have a real part of X, right? It has to be, it's best to be real, but cannot be completely real, because still the metal is absorbing. It has some absorption. The electric constant of the metal is complex. So when it starts propagating, part of the field is inside the metal, so it gets absorbed, but it propagates along X for certain distance. So the real part of Kx actually tell us that there is a propagating wave. It might be decaying because absorption, but it is propagating along X, decaying along Z, so it is a surface wave. And in order for this to be real, we can easily see that because the real part of the dielectric constant of metal is usually negative, then we need to have the absolute value of epsilon, of the real part of epsilon, has to be larger than the dielectric constant of the unaligned medium, epsilon A. So this is like a third condition. The second is the momentum matching. The third condition is on the value and the sign of the dielectric constant of the conducting medium, which is metal. And when it is conducting, usually epsilon is negative, at least in certain range of the spectrum. Okay, so as mentioned, we do have the the important parameter, which is called the penetration depth, and it determines important for the sensitivity, selectivity. So the penetration depth will be, if we calculate from here Kz, we can know what will be the penetration depth, 1 over Kz basically. And we can easily find also the propagation length along X. Because of the absorption, as mentioned, Kx has imaginary part. So 1 over the imaginary part will give the penetration depth. If you want it in terms of the intensity, then we have a factor 2 here. As we can see, there is the importance of the ratio between the real to the imaginary part of the dielectric constant of the metal. And when it is large, then the propagation is larger. Usually is better. It gives us higher sensitivity, higher, let's say, a figure of merit of the sensor. And even in localized nanoplasmonics, this ratio is very important. It also gives higher enhancement when the ratio is larger. The larger the ratio, the larger the enhancement factor. And we will show some rough approximation. We will show this analytically. Okay. So if we plot the propagation length, for example, the red curve and the penetration depth, the blue one, for silver, we can see here that the propagation length can approach tens of microns in the visible range, or could be hundreds of microns. And in certain cases, you can design a structure which can be even larger. That's called then long-range plasmons. And these can be important for information processing, like photonic circuits, for example. However, for plasmonics, we need to control the penetration depth mainly, because if we have a variety of bioentities, both molecules and cells, we need to be able to measure all of them. And as we see here, if we increase the wavelength, then the penetration depth it increases more than linearly. Yeah? That's because of the dispersion of the refractive index of the metal. We can see if we work in the near IR, it becomes like 1 to 2 microns, which can be good for cells, for bacteria, for example. While when we work in the visible range, it's less than half a micron, so it could be problematic for detecting bacteria. Okay, the matching condition can also be seen on the whole issue of the sensitivity of the wave to the variation of the refractive index of the medium. It can be seen from this expression, where if we plot it versus, like we convert it into type of dispersion relation, we have the omega versus k, the frequency, we normalize it to the plasma frequency. We normalize the kx to the plasma wave vector, kp, and we get this dispersion relation in a normalized form. So when we plot it, we find this curve like the green one or the red one. And the idea is that the light will come with dispersion relation, which looks like this. Omega is linear with K, right? In air or in standard isotropic medium, it looks like this. So it does not intersect the dispersion curve of the plasmon, and we cannot excite the plasmon from free space. In order to be able to excite it, we need to change the this angle here, the slope of the dispersion curve. And for that, we use the coupling medium. That means omega versus k. It means we need to have here a factor which will give us like a smaller angle, so a smaller angle, okay? So if we do that with a prism, we can easily write omega normalized to omega p, like the kx normalized to kp. And here we have sine of the angle inside the prism. We can, if we choose a prism with large enough refractive index, then we can get this slope here small enough to get intersection with the dispersion curve of the plasmon. So the condition for excitation will be met at this point. If we change the refractive index of the analyte, it will shift to this point. Okay, so we get this shift, and what we measure is actually the whole curve, the spectral curve or angular curve. Now we can measure the angle or wavelength or intensity. There are many modes we will talk about. Yeah, experimentally, it's a very easy setup. You can have the thin film on top of a prism, and then having a collimated light and varying the angle and measuring the reflectivity with a photodetector if you want angular mode, or spectrometer if it's a spectral mode. So you look for the resonance in the wavelength or angle and look for variations of the shift of this resonance with the refractive index of the medium here. This is a simple plot where you can easily plot reflectivity versus angle or versus wavelength. And you can even estimate the sensitivity analytically. The angular one, it looks like this, and the spectral one looks like this, which means giving something like, in this case, something like tens or 100 till 200 degrees per RIU. And the spectral one can arrive to few tens of nanometer, few tens of thousands of nanometers per RIU, even 50,000 sometimes. And if we calculate easily to what refractive index, what will be the minimum refractive index that we can measure, we can estimate that quite easily, depending, of course, on the noise of the system. But typical systems can go down to 10 to minus 6, and even with some care could be 10 to minus 7 RIU, which corresponds to 1 picograms of material per unit area of millimeter square. That's very small. In terms of concentrations, it's like 0.1 nanograms per milliliter or even less. Okay, so we have been working with improving the performance of SPR sensors, both the extended and the localized, and improvements in many ways. So in order to improve the sensor, we need to look first, how the response looks like. So we are measuring a spectrum, could be angular or spectral, wavelength spectrum. And there is something called sensitivity, how much sensitive this curve to the variations of the refractive index of the analyte medium. So the sensitivity for small variations is like the shift in the angle versus the change in the refractive index. The same with the spectral one. or maybe we can measure intensity, as we see here. If the curve is very narrow, then we get a very big change of the intensity. So the intensity sensitivity will be delta R over delta N, which can approach like a very small shift of the width of the spectrum of the resonance will give us almost 100% variation. So the narrower the resonance, the more sensitive it is in terms of intensity. So it means this width is a measure of the quality of the sensor by the end. So it is, people define the figure of merit almost like any other resonance, is given by the sensitivity divided by the full width at half maximum. So the larger the sensitivity, the better. The smaller the width, the better the figure of merit. And you can easily think about it because if the full width half maximum is very large, it will be like a very wide spectrum. And if it's slightly noisy, then you will have large error in determining the minimum of the resonance. Okay, so it depends also in your system. That's why we define here something called, the detection limit, the resolution of the sensor will be the minimum value that we can measure. So the minimum shift will give us the minimum refractive index that we can measure, which means the minimum concentration of the analyte. So if we have the minimum value of the angular shift, let's say delta theta minimum, or wavelength delta lambda minimum, like the resolution of a spectrometer, we divide by the sensitivity, because the sensitivity is defined by this shift versus the change in the refractive index. So if we take delta theta minimum here, will be delta N minimum here, which means like the detection limit is determined by the signal when it becomes roughly comparable to the noise. So when we have signal to noise ratio, almost 1. Okay, you can argue, maybe make it twice, like having SNR equal 2 or 3 to get more reliable result. But more or less, it's determined by this relation, which means if I have larger sensitivity, I get better resolution. If I have a better system, I get better resolution. And also if I have narrower resonance, then the minimum delta theta I can measure will be better, and the same with the minimum delta lambda. But what happens if it's very, very narrow? My spectrometer cannot resolve it. So it means it's not helping me anymore. I cannot measure it because I need a more sophisticated system. So there is a trade-off between this requirement, what do I really want, and the cost of the system by then. If we have this curve very narrow, we need a high resolution spectrometer. Maybe we need much more precise angle measurement. So the beam has to be much cleaner, and we need very fine rotation stage and so on. So the system becomes more expensive. But it depends on your requirement. If you do not need this high resolution, like very low detection limit, then you can choose, for example, standard off-the-shelf spectrometer, and that's good enough. Okay, we can do the same for the reflectivity, and some people also measure the phase We will talk about it later. But in conclusion, we can say there are, you know, like with any system, there are the parameters that come from the physics, the optics, the materials of the structure that we are working with. These give us the sensitivity. There are also the system requirements, which are basically like the signal to noise ratio of the system. Okay, we have been working with this a lot. We started with this methodology of reading the signal by simply using a diverging beam. So we have a large spectrum of angles. And then we can measure them in parallel using a camera. So this way we don't need to do scanning. If you have a nice and a clean beam and a quiet camera, you can have a very high resolution. If you look at the image, it's not an image actually, it's more like a light distribution. Then you will see at certain angle, you will get a dark line, which corresponds to the resonance for this type of medium. In this case, we have like a channel, and there are two sides of the channel. One side has a water, the channel itself made of a glue, and the other side it has oil. So you see the three of them. The oil has this dark line. The glue also has a darker line. It's not very nice glue, so that's why the contrast is lower. And the DI water has its own line. If you calibrate the system, then you know which pixel you have, to which refractive index it corresponds. So you can calibrate the system, means finding pixels versus refractive index, and then you can find the refractive index of any other material. Besides, you can use the glue as a reference. Right? So if we think about it, now you have a complete line here and many columns. Each column gives us like one scan. So it means we have many measurements, and if we have many measurements, then we expect our detection limit to improve by the square root of the number of measurements. So using this very simple setup, we managed to improve the, in terms of the system, let's say, a simple system, and can give us 10 to minus 6 quite easily. And we demonstrated sensing of many things with it. This was bisphenol A in water, histrone in water, with detection limit of something like nanograms per milliliter. The latest one was a biomarker for stroke detection in water and in plasma. And this how the system looks, we try to miniaturize it as much as possible. It's made of two channels. Here we can have a flow and control the measurement, the medium that is flowing in the. It can have one reference channel and one measurement channel, as you can see here. By varying the concentration of the analyte, you see the signal is varying. This is called a sensogram. In many applications where you need to analyze the binding of one molecule to the other, to measure binding kinetics parameters like affinity and binding constants, you need to analyze this time dependence. And it's possible to do that. The company has a software to analyze binding kinetic processes. So we will continue with this issue of enhancing the sensitivity of plasmonic sensors, and we are not the only one here. There were many works in the past. I will mention part of them here. For example, if you play with the metal, some metals gives higher sensitivity. Combination of silver and gold was found to be the optimum. If you choose a prism with lower index, actually you get higher sensitivity. But there is a problem with each way. Each way you improve the sensitivity, there are other problems. I will not go over all of them because we don't have time, actually. And some people use the nano grating on top of the metal and get enhancement by a factor of 7. And then there's the long range SPR, where you have two plasmons, one on the bottom of the metal layer and one on the top. So the bottom one can be used as a reference, and the top one has slightly larger penetration depth. That's why it propagates longer distance also, because there is less field in the metal, so it gets absorbed less, it can propagate longer distance. It has the advantage of being self-reference sensor. And of course, there are other ways of doing it, like what's called phase-sensitive SPR, because the phase curve is sharper than the intensity curve, then you might be able to get a better detection limit. I will try to explain it later. This shows a metamaterial type structure, mainly columnar type structure, and shows higher sensitivity. Is more like playing with the metal properties, because it becomes like a composite metal with certain properties. You think about it like a metal with a lot of dielectric in between, so it is less absorbing. And that's why it becomes better, actually. So the phase one, if you look at the phase, like with any other resonance, usually there is a jump in the phase, and this jump is quite sharp, sharper than the resonance itself. So if you are able to measure the phase in some way, then you can get better detection. There are some arguments about this, because by the end, you're actually measuring intensity. So measuring intensity should give you, it should be determined by the signal to noise ratio. Well, it's true, but still, because of the sharpness, you are able to get better result. And if you do it with a phase shift, similar to phase shift interferometry, like giving 3 phase shifts between the 2 polarizations, you can extract the what's called psi and delta, the ellipsometric parameters, from 3 measurements. You can do it in parallel, then you get much better improvement. Besides, we found that this phase curve is less sensitive than, to the variations in the thickness of the metal itself. So you have less tolerances on the metal thickness. Okay. So the relation between the field strength and the sensitivity, that can be seen quite easily if we simply write the wave equation and take the case of a waveguide and say the mode has a k vector, and we look for very small variation in the refractive index of the waveguide and small variation of the k vector. Then within what's called first order perturbation theory, you can find that this shift is proportional to the overlap integral between the field before and after introducing the variation in the refractive index, which means it is determined by the end by the strength of the field. So the field strength should give us an indication of the sensitivity. which is determined by the geometry of the sensor, a nanostructure, localization, could be band gaps, material parameters, and so on, and also the interaction volume. So it means the penetration depth or the propagation length, or if you have like a porous medium, like the metamaterial we just mentioned, what's called porosity of the metal, let's say. We can make a porous metal and it will give us higher sensitivity, which can be explained based on the same integral. So we investigated this a little, and you can see here a quite nice correlation between the overlap integral, that's the blue curve, and sensitivity of a sensor, the spectral sensitivity. Sorry, actually it's the angular one versus wavelength, depending on the wavelength. And we did that for one special case where we have a metal, and on top of it, there is a small layer, like 10 nanometer of silicon, which we found it improved the sensitivity, and we wanted to explain it. Actually, that's how we arrived to it. So if we calculate the field for the standard SPR without the silicon layer, we get this one. As you add the silicon layer, you get here a factor of 10 almost in the intensity of the field. And this also improved the sensitivity. So that's how we arrived to this correlation between the two. Okay, this case we investigated more. If you increase the thickness of this top layer, you get like a waveguide structure. We will not go into it, and because it's a waveguide, you start to get also TE resonances, but these are not plasmons, these are guided modes. You still can use them for resonance, but we are talking about a very thin layer where you don't have a guided mode, only the SPR mode. And you can see here how the sensitivity increases as you change the refractive index of the medium. The shift becomes larger than the case where you don't have this additional layer. And it also, the sensitivity increases as you increase the refractive index of this top layer, which is why we use silicon, because it has higher refractive index. Then we find quite interesting result. As you see here, the resonance becomes wide. So the figure of merit might not change, actually. It almost does not change. The sensitivity is better, but the figure of merit is the same. Although you gain in the field, that's another advantage. But if you want to improve the figure of merit, we need to go to the spectral mode. And here we get quite interesting result. Is when we do that in the visible range, we get this improvement on the width of the SPR as we add the 10 nanometer silicon. But when we work in the near infrared, we see a drastic variation. And it's not far away wavelengths. We can easily use off-the-shelf spectrometers in this range these days. So it is doable, and you improve your sensitivity and figure of merit. Because it's in the NIR, you improve the penetration depth, so you actually can detect bacteria. And this shows that the signal is monotonic with the bacteria concentration. As you can see here, the shift is monotonic. When you do that with the standard SPR without the 10 nanometer silicon, then you don't get a monotonic signal. Okay, we also mentioned the porosity effect. And actually, we were guided by this correlation between sensitivity and overlap integral. We wanted to prove that the porosity actually improves the sensitivity. So we went into this methodology of producing porous metal by oblique angle deposition. when you deposit at large angle, you start to deposit the material, and then because of shadowing effect, it starts to grow in columns. So it means you have like a porous material. These columns are nano columns, actually. They have a width of like 20 nanometers. So actually, the scattering is quite small. They are close enough, like 10, 20 nanometer voids between them. They are random. It's still conducting, depending on the porosity, of course. But so you can get surface plasmon, extended plasmons from this structure, but you might also get a localized one on the tip of the nano columns. So you can win in both directions. First, we went into the extended plasmon to prove this claim. And we were surprised, actually, to see very nice resonance at 10, 20, up till almost 30%. And the sensitivity does increase as you increase the porosity. But if you increase more, this resonance becomes very wide. So it becomes useless, actually. You can think about it. When the porosity is large, the metal is not conducting anymore. So it's not a good metal, actually, and you will not get a good extended plasmon. But maybe you start to get a localized one. So if you can easily calculate sensitivity for this composite structure versus porosity, and the simple calculation showed indeed that you can get almost 3 times improvement in the sensitivity if you increase the porosity by 30%. And also the correlation with the field, it shows very nice correlation. As you increase the porosity, you get larger field enhancement. So we proved the concept, and then we wanted to move to something else. Before we move to something else, like the localized plasmons, we will talk about improving or controlling the penetration depth. As mentioned, with a small penetration depth, we can measure up till viruses, which are like tens of nanometers. But if you want cells, we need larger penetration depth. And in order to do that, we went to a structure, it's a multi-layer structure, which is similar to the configuration I mentioned for long-range plasmons, where you excite another plasmon on this interface, and you can use it as a reference. But the astonishing thing is that if you add additional layer here, it acts as a waveguide, but then you can tailor the parameters so that the mode has a very large penetration depth inside the analyte. So you can see here the extension of the field can arrive to like a few microns, 6 microns or something like that inside the analyte. So you can put one biofilm or 2 biofilms or even more and monitor its growth. Besides, this sensor is self-reference, so this peak, this resonance, which corresponds to this interface, does not move as you change the refractive index. So you can use it as a reference. And besides, for the air, you still can see the resonance. So you can measure gases, liquids. It's self-referenced. Here it becomes very narrow. So you get improvement of the figure of merit, and you can control the penetration depth. So this shows a result we get with cell phone, I think. It shows the self-reference resonance is not changing. And the other resonance, it shifts from air then to something like 1.3 to water and to ethanol. As you can see here, it becomes very narrow. So you need much better beam quality in order to see, right? Because it becomes narrow. But this goes back to the original requirements. When you have a very high figure of merit, like very narrow resonance, you need a better signal to noise ratio, right? To be able to resolve it. So here we can see that we can resolve it still till ethanol, which is quite good dynamic range. Okay, if we go to, before we go to nanoplasmonics, we would like to do something called a transition from extended to localized, from plasmonics to nanoplasmonics, let's say. And we do that by having periodic structure. Why? Periodic structure is like a grating. It gives you extended plasmon, but on the tip of the, let's say the grating, on the tip, on the edge of the lines, or could be on the edge of a prism, it can give you localized plasmons, right? So it's a kind of, should be some transition between the two regimes. And we
Professor Abdul-Halim,
yes?
I'm sorry to interrupt you, but we...
Yeah, we have to finish. Okay. So,
yes, and leave some time for questions.
yes,
okay.
we'll finish this one and then we'll jump to the summary. Okay. So with this one, we have a grating, a nano grating, which gives also because it's very thin, we found that it gives two resonances. Again, one is used as a reference and one is sensitive to the analyte. As you see here, it works in transmission. So this is called the the extraordinary optical transmission through nano holes or nano slits. But here we found that if we use the grating to be very thin, first of all, you improve the transmittance and also you get self-reference. And this is the proof of it. And you can enhance also the field quite largely. So you can use it for enhanced spectroscopy. So I will not have time, unfortunately, to talk more about nanoplasmonics. So I will jump to the summary. So to summarize, plasmonic biosensors have a large growing market have applications in many fields: environmental, pharma, food, and health, like medical. Of course, it's a very interesting topic. The SPR physics, the optics, allows many different modes with variety of improvements in the performance. All can be correlated with the electromagnetic field distribution. And we can miniaturize SPR systems so they can be portable and low cost. So are suitable for point-of-care devices or even maybe home devices. For the future, we need to work still on the specific sensing protocols, like how to design these antibodies, aptamers, or peptides to bind to the specific analyte that you want to detect, to be highly selective, because inside mediums like blood or plasma or water, there are many analytes lying there, many pollutants or biomarkers, and you want to select the correct one. So this is the main issue now, the bottleneck, I would say, for getting specific sensors. Thank you very much. So if there are questions, we'll be glad to answer. Could also be by email. Thank you.
So it's open now for questions, please. All right, I think it was very interesting lecture. Thank you very much, Dr. Abdul Khalim.
Okay. So it was.
And I hope that we will have one more.
Yeah, I hope so.
Okay, thank you, and thank to all the audience. Thank you.
Yeah. Bye-bye.
Bye.